Hey everyone, this is Brian, recording another video lecture for CSC 143. In today's video, we're going to be learning about hashing, maps, and hash maps. We'll start out with a discussion on hashing and maps. Throughout this course, we have explored several ways of storing and sorting data. Associating, or mapping data, is another significant problem in computer science with real-world implications. Students are mapped to their grades and the classes they take. Patients are mapped to the medications at a pharmacy. Products are mapped to prices in a store. Employees are mapped to their salaries and their job titles. We've seen some ways we can associate data to other data already. Class references, instances that is, are mapped to their properties. A school instance is mapped to its name property, which I can perhaps retrieve by invoking the getName method. The pair class that we've seen, which has a left field and a right field, associates a left and a right value. One way of looking at a pair is like saying the left field of the pair corresponds to the right field of the pair. Inside an array, indices of the array map integers to the values that are stored inside the array. So for example, index 0 at the first element inside the array is kind of like saying 0 maps to the first value, or n maps to some value inside the array at index n. One way to think about this is like a lookup table in Excel, where you have a grid of cells where each cell is uniquely identified by its coordinates. We can think of the coordinates mapping to the value inside the cell. Paths in a tree are associated to their endpoint values, like navigating in Google Maps. If you start from one position and you intend to go to another location on a world map, the path to that location essentially maps your position to the position that you intend to go. Now, for clarity, there is a distinction here between something like a world map and the act of mapping. In computer science, when we talk about maps, we typically talk about the association of data. That is, one thing maps to another thing. Unfortunately, there is a certain name collision here where when you hear the word map, you kind of also think of a world map. This is an unfortunate coincidence between the names of these things. In this lecture, we're going to be talking about mapping data from one entity to another entity. Now, we know about these structures like arrays and trees, but they're not general purpose. I mean that in the sense that arrays can only map integers to values, not some generic type to another generic type. For example, let's say I had a name that was in a string form, and I want to associate it with an address that's also in string form, like the name of a business and the name of its address. I can't do that with just a basic array, because I only get integer indices that map to values. So it's not really helpful to say, go to store number 57, right? That's not super meaningful, even if the address is stored at index 57. It's very hard to remember the number and its mapping to its value. Instead, we would much rather map the name of the store, like restaurant XYZ, to whatever street address it currently exists at. Trees also don't let us do that. If we have a tree, we have to carefully arrange the data for efficiency purposes, such as with binary search trees, and the actual paths may not be super meaningful. The path from the root to a destination inside the tree may not actually have some physical meaning that it corresponds to that maps the root to that node in the tree. With that in mind, let's come up with an interface in Java that essentially lists out our desires for something that can map something to something else. I'm going to call that table.java. Let's take a look at the operations we might consider inside of a map. Here's my public interface table. It's a generic interface. It's got two generic types, k and v, and it extends the iterable of pair interface. We'll get to this in a second. In my table, I want two things. I want to be able to get values that are associated with a given key, and I want to be able to insert and associate a key with a value. So we're going to use these two generic types, k and v, to reflect the type of key and the type of value, respectively. And our table is going to associate keys to values, just like how in Excel we associate grid coordinates with values inside the grid. Really, the most pure operations that we require out of a table-like structure is being able to insert items into the table at a given key, the value we're going to associate with that key, and then retrieving the value associated with the key using this get method. Now let's talk about this extends iterable of pair key value. If you haven't learned already, you may have seen this in some locations in the Java standard library. Interfaces can extend one another. We didn't really formally talk about interface extension, but you can probably surmise what this means. When an interface extends another interface, it essentially inherits all the public abstract method declarations that are inside the interface being extended. And the outcome of that is it's sort of like merging whatever abstract declarations are currently in iterable with the abstract declarations that are defined in the child interface. So table now has not just these two abstract declarations, get and put. It's also going to have these abstract declarations that are defined in iterable. And we know what the iterable interface is like. It basically has an iterator method that is going to return iterators when invoked. So whatever class chooses to fulfill table is going to have to fulfill get and put, as well as the iterator method. So you can iterate over a set of pairs of types k and v. Now, why would maybe want to iterate over a table? What purpose could this serve us? We're going to make table an iterable type so that not only can we retrieve individual values outside of the table and insert values, we can also walk all the values within the table. So this is akin to opening an Excel spreadsheet and pressing the down arrow key or like scrolling down through the sheet to read through all the cells within it. We would like our table not just to be a store of data that associates a key to a value, but also be something that we can examine from front to back to look at all the keys and values that are currently stored in there. And we're going to do this. We're going to do this by saying this table is going to be an iterable type, and the type that is being iterated over are these pairs of keys and values. So that every time I take a step, I get a pair that associates the key and the value, kind of like if I was in Excel and I was scrolling down, I get pairs on the way out of iteration that on the left of the pair is going to be the key, which is the coordinate, and on the right of the pair is going to be the value, which is the value stored inside the cell. Okay, so this is just an abstract interface. I've got some method declarations here, and I'm going to use this abstract interface as a way to motivate our discussion on how we want to implement a table-like structure or a map-like structure. So we could fulfill this table interface and make arrays be general purpose by storing pairs of elements inside. One example of this was like in project 1, where I had you store recipes that were composed of strings and integers, where the string on the left was the name of the ingredient and the integer was the quantity of the ingredient involved in the recipe. This array list of pairs is akin to someone reading aloud to you the things that you have to put inside the pot when you create the food item. So we can fulfill this table interface, the need for a get and a put method as well as iteration, by just having an array list structure that stores a whole bunch of pairs where each pair associates some key and some value. Let's go take a look at how that works. Okay, here's my array list table declaration. It's got two generic types, a type K and a type V, which are for the key type and value type respectively. And I'm going to say it implements the table of KV interface. So now I've got the obligation of this child class to fulfill the get and put method as well as the iterator method inherited by table. And we're going to do so by having this essentially one-dimensional table that stores pairs inside. I'll call that table just be lowercase table here. And I will fulfill my get and put methods just using iteration. Let's examine put first. What we will do is we will try to iterate over the current pairs in the table if we happen to find a key that's already in the table, we will try to assign it to the value we're trying to associate. Otherwise, we will insert that value into the table using table.add. And I'm sure you saw this little message here. This example code only, do not use. The reason I put this here is because this is kind of the first approach that we might try taking. And I'm going to try and uncomment out this line here, and you're going to see why it doesn't quite work. So again, the put method is either going to insert a new pair that associates a key and a value, or it's going to replace whatever value is associated with the existing key, if that existing key is already present inside the table. So to take care of the override step, my first intuition might be to iterate over all the pairs in the table, and then if the key of the pair I have iterated over equals the key that I currently have when I'm calling the function, let's replace the right field of that pair with the value that I have in my hand. Unfortunately, the pair definition is not going to let us do this. We get this error that says cannot assign a value to a final variable right. And if I control click on my pair and go take a look at what that means, actually I can go control click on the right property. What I see is that there's this final keyword here in front of the keyword public. What the final keyword does is it enforces that as soon as this field has been defined, it can never be rewritten. So when the pair is constructed and this.right gets assigned to the right argument of the constructor, the right field can never be replaced again. This is an intended design. I had done this so that one day we could talk about what this hashcode function does. And we'll get to this actually pretty soon. But for now, we're going to treat this pair as if it's only going to have immutable left and right fields. As soon as left and right are defined, we cannot modify them. One advantage of immutability, that is, having these constant fields, is that anytime you see a reference to a pair, you are guaranteed it will be the same pair object underneath for the lifetime of that object. When I construct this pair with the left and right field, and I reference it in several different locations, maybe I put it inside of a list like I'm doing with the ArrayList table, I'm guaranteed that that pair will always be the same pair in terms of the values it contains. There will never be a circumstance where I examine the pair, I look away, I do something else in my program, and I come back to that pair instance, and I see that the left and right fields have changed. If I need to create a modified version of this pair, I have to actually build a brand new pair, and this new pair is going to live at a different location. So any prospective clients of pair can treat an existing pair as constant and any new pair instances as new pairs. Let's go back to that ArrayList table and see what the effect is. Here, because the right field is immutable and I can't modify it, I can't actually modify and replace its value in place. This code is not going to compile for me, which is why I put this example code only, do not use. It doesn't quite let me do it. However, I would still like to replace this pair right here if I am trying to overwrite a value that's associated with a given key already in the table. I want to eliminate the existing pair because it takes up space and I might accidentally read from it and rewrite it and overwrite it, replace it with a different pair. Here's how I'm going to do that. ArrayList is a list. List provides the list iterator. That is, if I invoke iterator upon list, it's going to provide me a specific iterator type called list iterator. And as it turns out, list iterator has a method called set that lets us replace values in place on the list. Here's how I'm going to do that. I've got my table, which is an array list of pairs, and I'm going to invoke the list iterator method on it. And that's going to give me something called a list iterator on the way out. A list iterator is a lot like an iterator. It's got that next and has next method, but it also has a method called set. And what set is going to do is it's going to replace the value that I'm currently iterating on with the value that I'm going to pass into the argument. The set method is kind of like the remove method that we've seen in the past, where remove is going to do an in-place removal of the item we're iterating over. List iterator's set method is going to do an in-place replacement of the item we're iterating over. So, just to recap, our put method is going to do one of two things. It's either going to associate the value with this new key, or it's going to replace the associated value for an existing key with the value that we're passing in here. So if the key does not exist, we insert a new pair associating to the value. If the key already exists, we're going to update the value associated with the key that we're passing in here. We are taking care of the update step. So I have this list iterator, and I'm looking for the pair that currently contains the key that I'm trying to override. I'm going to start pulling out individual pairs from this iterator. I'll do a simple loop structure. I'll ask, so long as the iterator is no longer exhausted, I still have values. Let's go ahead and pull a pair out. I've got this pair with a key and a value. And if this pair currently contains the key that I have stored, let's go ahead and replace that pair with a brand new pair that has the same key but a different value. This is going to completely replace the reference that's being stored inside the table at the location I'm iterating over with this pair instance. And what this is going to do is it's going to ensure that I'm never going to have more than one pair that has a given key inside my table. That would be bad, right? That would be akin to having an Excel spreadsheet that has a cell that has the same coordinates as a different cell, even though they have the same coordinates. It doesn't make any sense. I want to have one set of coordinates per cell. I never want to have more than one cell per coordinate inside my spreadsheet. Similarly, inside my table, I never want to have more than one pair that has a given key field inside the table. So this is going to take care of our replace step, where I'm trying to replace a value that's already existed inside my table and associated with an existing key with a new value. If I do not intend to replace, that is, the key is not already present inside the table, I will reach the end of this loop, and I will have missed this condition where there is already a pair that has the key I'm looking for. If that's the case, it's time to add in a new pair to the very end of my table. I will do so using the simple add method on the array list, which appends to the end, and I will append a new pair that associates the key and the value. Okay, so what this block of code is going to do for us is it's going to let us build up a table of items that simply has keys and values as these pairs. And it's going to store this in a linear way such that anytime I want to go look up through this table to see if a key already exists or find the value associated with the key, I'm going to have to perform this style of iteration of looking through every single pair to go see if I have a key that already exists in one of these pairs. And that is what my get method is going to do. This get method is now quite a bit simpler because of all that work I did in the put method to retrieve a value associated with a key. Let's go ahead and just iterate over all the pairs inside the table. And if I find a pair that is housing the key that I'm currently asking about, then I'll go return the payload that's associated with the key. So going back to that restaurant example, when I passed you a list of pairs as a recipe, the get method is akin to asking how many slices of bread do I need? How many pieces of meat do I need to make this burger? The key here is the name of the ingredient, so slices of bread, and the value that is associated with the key is the quantity of item that's associated with that ingredient. To determine that, all I have to do is walk this table that is composing my recipe. I'll go determine which of these pairs, these ingredients, has the name that I'm looking for by invoking the equals method on the left field, which stores the keys, and then I will return the right field, which is the value associated with the key. Okay, so that fulfills our get and put methods for our table, but the table is also an iterable type, which means I need to supply an iterator of pairs. And I'm actually going to take the easy way out here. To fulfill the obligation that the table has, which is that it is an iterable type, I need to supply an iterator. Fortunately for me, the ArrayList is already an iterable type, so I will just return its native iterator. So whoever invokes iterator upon the ArrayList table class is going to get the native iterator from the ArrayList that is housed inside this ArrayList table. Okay, as a little example of how the table is going to work for us, I went ahead and wrote this main method inside this class that you can run just as a small exercise. Here I've declared my people age mapping from string to integer as a table type, and I'll fulfill it using the ArrayList table that I just made, this class. Let's go ahead and associate some names and ages. Let's put in John, Alfred, and Bruce and have their ages be 20, 70, and 40 respectively. Then I'll go ahead and walk the people age table and print out the keys and their associated values, so the names and their ages. Then I'll see what happens if I replace a value already associated with the key inside the table. So Alfred started out as 70, and this line here is going to replace that value 70 with 81 for key Alfred, and I'll make sure that it updates my table. Let's go ahead and run that and see what happens. Okay, my table starts out as the keys and values I'm expecting. John is 20, Alfred is 70, and Bruce is 40. Then I replace Alfred's age with 81, and the put method is going to go find the key that's already associated with Alfred, or the key that is Alfred inside the table, and it's going to update the value associated with Alfred by replacing the pair inside that location, such that Alfred now has an age of 81. I've got some extra lines of code down here. We'll get to this hopefully in a couple of minutes. This table test is just another examination of the ArrayList table. I have that same set of keys and values. John at 20, Alfred at 70, Bruce is 40. Then I'll assert that when I use the get method, it's going to correctly retrieve the values outside of the table. And then if I try to get a key that doesn't exist, I'll just get null on the way out. Okay, great. We'll talk about this hash code in a little bit. Okay, so we've done the job of fulfilling the table interface. We've taken an existing structure that we're familiar with. We've packed it such that it sort of becomes a one-dimensional table where each cell of the table stores a key and a value. But there's a pretty glaring problem here, which is that unsorted lookup is O of n. That's not good. Anytime we try to use that get method and look up a value associated with the key inside of our ArrayList table, we have to walk the entire ArrayList, linear time performance, and that does not scale particularly well. We could sort it, but that requires the data be comparable in some meaningful way. Not all data is necessarily comparable. Remember, we'd like a generic structure that's going to map a generic type to another generic type. And not all those generic types are necessarily comparable types. There's no, perhaps, natural ordering to some things in the world. Like, you cannot naturally order all the animals on the earth. There's just not a natural order like we see with numbers or something else, like strings. If we did use a balanced binary search tree as a backend container, assuming it was comparable, we sorted it by key, lookup would be log of n, not too bad, and insertion would be log of n. So, slightly less horrible, but also not super ideal, right? Log of n is good, but it's not amazing, and okay, log of n is pretty amazing, don't get me wrong, but I really would like to see O of 1 in one of these locations, kind of like how we saw O of 1 in the heap. The other thing is the binary search tree is also going to require that this be a comparable type, because I have to be able to order it in a particular way. Before we dive into the nitty-gritty details of what we want to do, I do want to say that two keys that are equal each other by value should map to the same value. They don't necessarily have to have reference equality. If we only used reference equality here, that would require two keys to have the exact same memory location, then the following is not going to work. Table.getJohn equals table.getJohn. These two string instances are two independent string instances. They will be constructed in two different locations, but they will not permit this expression to be true if my get method depends on reference equality, because maybe the left-hand John is going to be different in terms of reference equality than the right-hand side John, and get is going to treat these two keys as two different things. We do not want this to be the case. We would like this expression to be true. We would like this equality to hold true, but we don't want our key implementation to assume that two keys that are not reference equal are not the same. Let's go take a look at that ArrayList table again, just to be sure and clear what I mean. A, B, and C are all the string hello world. However, they are not all reference equal. I cannot say A equals B, because that's not going to be true. These are two, well, IntelliJ tells me it's not a statement, but you know what I mean. This is not going to hold true because A is a constructed string hello world and B is a separately constructed string hello world. Even though these literals look the same, they are value-wise the same, they are physically different. They are located in different spaces in the world. Despite this, I would like to be able to say something like peopleAge.get of A, peopleAge.get of B, and be able to retrieve the same value on the way out. Thus, our table implementation should not care about the references that exist for these objects. Instead, they should care about the values that those objects are storing underneath. So retrieving a value of the key hello world should be the same whether I pass in A or B. I believe I also look at that in the table test. No, that's hashcode. We'll get to that soon. Okay, so now that we've talked about how our existing structures have sort of failed us, I want to dive into the subject of hashing and how hashing is this sort of magical technique that's going to get us super fast lookup and potentially fast insertion speeds out of these generic types that are not going to be limited in any way, in that they don't necessarily have to be comparable or something else that's specific. And we're going to get into this discussion by starting out with an observation that arrays are O of 1 lookup tables with integer keys. However, arrays are O of 1 lookup tables with integer keys. We have a very specific key type, that is, it must be an integer. I'm not allowed to use anything else. We want lookup tables that map generic keys to generic values. So here's the big idea. If we can map generic keys to integers in O of 1 time, then we can map those integers to values in O of 1 time, because we know the array can do that for us. So our step is going to go like this. It's going to go from a generic key. This generic key can be of any type. It can be a string, it can be a pair, it can be a list, it can be whatever. I'm going to map that to a number, and then number is going to be mapped to a generic value. That means we only need a single array lookup table that stores values. But we're going to have to find a way to get integers out of keys, which can be used, or which the keys can be of any generic type. Those integers will be indices into an array that will locate the value associated with the key. Let's call the method for transforming a key into an integer hashcode. My first attempt to fulfill this hashcode implementation is a little bit naive. I'm going to try to map all the keys to be some random integer. So when a client has an instance of this person class and it tries to invoke the hashcode method, it's going to get some random number on the way out. Okay, so that accomplishes the first task of needing to associate every instance with some number. Then inside my ArrayList table, I'm going to use that number inside my get method. So once again, my table is a backing structure that is an array list of pairs where each pair is an associated key and value. And my get method attempts to determine the value that is associated with the given key. And now that I have integers for every key, which is defined by its hashcode implementation, I can use the native table ArrayList get method, which is going to go look up the value at the specified index, and that's going to give me the pair at the index indicated by the keys hashcode, and I'll return the right field of the pair, which is of course the value that I'm trying to look up. What you'll see with this get argument that I pass to it is that the expression is a little bit more complicated than just key.hashcode. In fact, it's key.hashcode modulo table.size. And remember that the modulo operator is the remainder operator. It's going to try and divide the expression on the left by the expression on the right, and if there is a remainder, that is, the expression on the right cannot wholly divide the expression on the left, then that remainder is going to be expressed by the result of the expression. So some examples, 12 modulo 4 is going to get me 0 because 4 can divide into 12, but 12 modulo 5 is going to get me 3 because the closest I can get is 15 when I have multiples of 5, and 15 minus 12 gets me a remainder of 3. So in effect, what the modulo operator is going to do is it's going to enforce that whatever hashcode returns, the space of integers returned by hashcode is going to fit somewhere as an index into this table. If we look at the return type of hashcode here, is that it's just an integer in Java. And the space of integers in Java spans something like negative something billions of numbers to something positive billion, right? So the return type itself is not expressive enough to indicate the more specific space that we're looking for, which is indices that fit within this table. With that in mind, we need to enforce that this index does indeed exist inside the table. So the modulo operator is going to essentially compress this space that's returned by hashcode to fit within the range of 0 to table.size -1, which is the span of possible remainders that I can get out of dividing an expression on the left by the table.size. Another way to think about modulo is kind of like a clock. If I told you to compute the time from 72 hours from now, and you looked at a wall clock and the hour hand was currently set to some value, you could traverse the wall clock in 12-hour circles, something like 6 times, until you finally reach the destination of the hour hand. That's kind of what the modulo operator is. It's kind of like how the clock is going to compress that number 72 into the space of 12 and map the number 72 to a value that fits within the range of 1 to 12 on that wall clock. So here, key.hashcode, regardless of what this number generates for me, it's going to be mapped and associated to some value that exists in the range of 0 to table.size -1 inclusive. Okay, so that's what my indexing is going to do. It's going to take that hash code, modulo the size, so I get a index that is actually valid inside my table, and then I'll return the right field, that's the pair that exists at that index. Now let's ask ourselves if this actually works. Is the hashcode function O of 1? Indeed it is. It is very easy for me to generate random numbers. Is the get method O of 1? It is yes, because the get method on ArrayList is O of 1, it's just indexing. Now what's actually wrong with the solution? A lot of things. The hashcode implementation is unpredictable. Every time I call it, I get a different index. That obviously doesn't make sense. It's like a cell that moves on its own inside Excel. That's not going to work out in the long term if I try to look up the same cell more than once. Another problem is this collision problem. Two people can share the same hash code and replace each other in the same array index. So if we happen to get unlucky and hash code returns something like 10 for one instance of person and it also returns 10 for another instance of person, the get method is going to confuse the two instances because the index that's returned by this expression is going to be the same for both of those instances. So we have this issue of unpredictability. That is, every time we call hash code, we get a random number. That's not going to scale up. Every time we call it, every time we try to look up the same instance, we get a different field, obviously not right. And we also have this collision problem where we could get unlucky and two instances collide and they map to the same pair inside my table. Okay, let's try to make this a little bit better. Attempt number 2 is going to still map all the keys to random. So let's ignore the unpredictability problem for now, but let's try and fix this collision problem by storing a 2-dimensional array and then walking the list for duplicates. Let's take a look at what I mean. I still have that random implementation for hashcode, so every time I invoke hashcode, it's going to return a random number. Again, in this solution, in this attempt, I'm not going to try to solve that randomness problem. Let's get to that. Cross that bridge when we get to it. But in my ArrayList table, I'm going to try and solve the collision problem, where two instances of person can potentially have the same hash code. So here, what I'll do is in my table, rather than storing just an ArrayList of pairs, I'm going to store an ArrayList of pairs, which is a two-dimensional table. So every index in the outer ArrayList is actually storing another ArrayList, which itself stores several pairs of keys and values. Then inside my get method, I will start to walk the table row that is associated with the hash code returned by the instance of the key. That's going to give me a list of pairs that potentially are associated with the key. And then I will ask if the left key, if the field on the left of the pair, the key, is value-wise equal to the key that I'm passing in. And if that's the case, return pair.write. This is actually going to solve our collision problem for us. Even if two keys have the same hash code, just by chance, if they don't have the same value, it's okay. One key is not going to collide with the other because this guard statement is going to check that the key I'm passing in is indeed equal to the pair that I'm currently examining. And only if that's the case, I'm going to return the value on the right. Otherwise, I'll do something like return null. So in effect, if keys in my table have the same hash code, they will bucket together in the same row. And it's okay so long as those keys are not value equal to each other. If they are value equal to each other, we already had this discussion, we're going to treat them as actually the same. So if that's the case, that's okay, I'd return the right value. If they're not the same, then I'm not going to return the value associated with the pair, so I'm in a good state here. Each index will store an ArrayList of its own key value pairs. This way, if two person instances ever hash to the same index, we can walk through each pair in that list and compare the actual person instances with the keys in the pairs to determine the associated value. Now let's ask ourselves if this makes sense as an implementation. Is hashcode O of 1? Yes, it still is. We're still returning random. Is get O of 1? No, not really. I have a for loop here. I potentially have to walk up to n items inside my table, even if I'm only examining a single row. So I've degraded my performance because my get method has to look down a linear list of elements, and I get something like O of n rather than O of 1. So what's wrong with the solution? Well, hash code is still unpredictable. That's not changed. I still return random numbers, so that obviously needs to get fixed. The get implementation is unlikely to retrieve the value that is stored because the hash code always returns random. Another thing we want to concern ourselves with is this idea of bucketing. If I accidentally and get unlucky pack all my key value pairs into the same row inside my two-dimensional table, I'm going to get degraded performance. And just the nature of this hash code being completely random, even if I have two instances that are actually value-wise equal, they're likely to end up in different buckets. So I really need to solve this unpredictability problem. Okay, let's try another thing. My third attempt is going to map keys to user-chosen value at construction time. Okay, here's how that looks. Here's my class person, and inside the class person is a new field called hashcode. Then when I construct the person, I'm going to pass in the static hashcode, the unchanging hashcode, the constant, to be assigned to that hashcode field. Then my hashcode method is just going to return that constant value that I've assigned inside hashcode. My ArrayList table is still the same. I have a two-dimensional table, which is an ArrayList of pairs. And when I try to look up a value associated with a given key, I will invoke the hashcode method on the key to get its index modulo the table.size, which gives me a list of pairs that all have the same bucket, the same index in the table. And if my pair's left field equals the key that I've passed in, then I know I found the pair that associates this key with its value, and I return pair.write. Otherwise, I'll do something like return null. Okay, now let's do the analysis. Is hashcode O of 1? Yes, because I just have a constant value now. I just return that, very easy. Is get O of 1? Sometimes. Get can be O of n performance if all my key value pairs end up in the same bucket. If I have n entries inside my 2D table and they all coincidentally happen to be in the same row, then my get implementation is going to degrade back to linear time. This can be possible because remember my hash code is a value that is passed in by whatever client is constructing hash code as some static value, as some constant value. And if whoever's constructing persons is being lazy about it and passing in a constant value all the time, like 0, just always passing in zeros, then every single person is going to end up in the same bucket. So even if I try to map different people that are not equal to each other into this hash map, into this 2D table, if hash code always returns 0 because the client was lazy and always passed in 0 to the constructor, then I still have to walk every single pair inside the entire table to get the value I'm looking for. So the unfortunate case with this implementation is that I've placed the responsibility of good hash code distribution onto the engineer who is writing the object instances that are being passed into this table. The hash code distribution depends on the developer. The developer can fall into this trap of passing in the same hash code to every single one of these instances and then degrading the performance of my table back to linear time. If all the instances use the same hash code, then get would be O of n. Performance degrades back to an array list of pairs as a table. With this interface, it's challenging to manually distribute hash codes evenly while also guaranteeing instances that are equal to one another have the same hash code. So remember that I said earlier in this lecture that if I have two instances that are equal by value, they should map to the same value inside my table. So if I have two keys of hello world, even if they are two different strings that live in two different locations in memory, if they are value-wise equal, they should map to the same value inside the table. Therefore, two keys that are equal to one another by value should have the same hash code. But this is not guaranteed by this implementation. A developer could define a person, pass in a hash code of 0, and define another person that is value-wise equal to that first person, but pass in a hash code of 1. That gives me two different people that are value-wise equal to one another, but mapped to different buckets inside my table. That's not good because ideally I'd like to be able to look up the same key value pair with keys that may not be physically the same but are value-wise the same. Zooming out a little bit, more abstractly thinking about this structure that we've defined is that the developer should not be required to accommodate the needs of a container structure when they define their class. When I define this person class, and I had this extra hash code field, the developer who's trying to use my ArrayList table is going to have to go about passing a hash code to every single person or whatever object they want to pass into this ArrayList table. This is a violation of the open-close principle. Classes are open for extension but closed for modification. If I have a generic container that maps generic types to other generic types, developers should not have to modify their classes to meet this requirement of the container. The container is its own class. The container has its own logic. A developer should not have to concern themselves with whether or not their instances can fit inside the container. Instead, they should just be able to define their own objects, and the container should be able to figure out how to organize those objects inside the table. Okay, so we've done a few things that don't quite work for us, but we've made a little bit of progress. We've talked about how we want reliable and predictable hash codes, but we also don't want to have too many objects collide with one another and impose the burden on the developer to come up with good hash codes. So what makes a good hash function? A hash is a function that takes arbitrary inputs and outputs values in a finite range. This is a formal definition, by the way. A hash is a function that's going to take arbitrary inputs and is going to output values to some finite range. Let's go take a look at the whiteboard to actually see a formal definition of how that function looks. A hash function maps a generic type t to some number, the natural numbers including 0. So another way of looking at it is hash of a key gets mapped to some non-negative integer. And in Java, that hashing function is this hash code method. The hash code returns a type integer. So here's an example. Let's suppose we are working in the universe of strings. I've got a whole bunch of different strings here that are names Abe, Brian, Ryan, and Joe. And I need to map this generic type on the left to some integer on the right. In Java, Java's going to provide me a hashcode function that's going to do such a thing. So maybe, for example, the string Abe maps to the integer 0, the string Brian maps to the integer 3, and Ryan and Joe both map to the integer 2. One thing to think about here is that the universe of strings is infinite. We can come up with any string in the world with any number of characters and letters and so forth. However, the space of integers is, in practical terms, finite. There are way more strings that we can represent in Java than there are numbers. And this is not the space of like big integers. This is more just like 32-bit integers or 64-bit integers. We can have a gazillion strings in our Java program, but we can only have so many numbers defined in our Java program. So the inevitability here is that we are going to have two strings that will map to the same number. And this is one of those problems that we can't actually quite avoid with these hashing functions. If we're trying to take the entire universe of generic types, which is unlimited, and we're mapping them to some integer that we can actually represent in our program, then we will inevitably see a collision between two generic types that have the same hash code. And we're going to see very soon that this is actually okay. So long as we have good randomness, that our output space of integers is evenly distributed, we can actually minimize the risk of two values colliding with one another. And we're going to see in our implementation that this is okay even if when there is a collision. So good hash functions have randomness. The output space should be evenly distributed among the space of the integers. The other thing we want from good hash functions is predictability. The same input should always produce the same output. We saw this kind of in our third attempt where we had a fixed hash code for all of our person instances. Therefore, every time I invoked the hash code method on a person, I always got the same integer on the way out. This is going to give us that value equals keys requirement that we had discussed earlier. Just because I have two different strings that live in two physical different locations in memory, so long as those strings are value-wise equal to one another, they should always map to the same hash code value. So the two things I want in my hash functions are randomness. I want to distribute those output values relatively evenly to avoid and minimize the risk of collision. And I want them to be predictable. Every time I have the same input to my hash function, I should produce the same output on the way out. Okay, now let's suppose we had that hash function with us. If we have this hash function, we can use this technique that we've learned in our last two attempts, which is this hashing with buckets strategy. We're going to store a two-dimensional list of key value pairs. We know what the pair type is. It associates a key instance with a value instance. We know what this outer list is, the linked list. It's a list of pairs where all keys happen to have the same given hash code. So this represents a given row inside my table. And then this outermost array list is my 2D table. It's a list of lists where each index corresponds to a particular hash code modulo the size. I've got those things written down here. Infinite inputs mapping to finite output space means that there will always be collisions where two inputs map to the same output. And in a good hash function, we want predictability. The same input should always map to the same output. And randomness. Output should be uniformly distributed randomly regardless of what the input is. A more refined definition of the randomness property is that similar inputs, like Brian, or Ryan, should appear randomly distributed in the output despite their apparent similarity. Without this kind of randomness, hash tables are going to degrade back to O of n lookup. So here we re-enter that discussion on not having the developer be responsible for having their instances be efficient in this container structure. Regardless of what the developer provides to me as key inputs, I should have an efficient structure that randomly assigns hash values automatically. This hash function design is a significant focus of study in computer science. So coming up with these hash functions is actually quite difficult. For this class, we will talk mostly about how we actually use these hash functions. The actual strategy for implementing hash functions is a little bit too advanced for this course. It is something that you might touch upon in a future course, such as with dealing with systems or algorithms. But for now, we are going to pretend and take advantage of the working hash code implementation that's given to us by Java. And we'll talk about this very soon. But for now, we'll pretend and assume that our hash codes are going to work as we intend them to. They're going to be random and they're going to be predictable. And we're going to build a hash table structure using this hashing with buckets strategy that we just discussed. Having pairs map keys to values, rows of pairs that have keys that have the same hash code, and then an outer table that manages all these rows where each row represents a hash code value that all the pairs inside the row are going to have as key hash codes. Now let's look at an example inside my diagram here. Let's suppose for a moment that my outer array list had 4 values, my n was 4, and inside each array list index is a linked list, where the linked list stores pairs of values such that the key in each pair has a hash code that associates with the index of that linked list. So going back to that first example where I had the 4 strings, Abe, Brian, Ryan, and Joe, we can start to fit in these strings into my 2-dimensional table based on the rules that we've described with this structure. So let's try to insert Abe. I say Abe maps to a hash code of 0, and the index 0 inside my array list has a linked list that stores all the pairs that have keys that have hash codes of 0. So here Abe is the only one. Let's say that Abe, I'd like to associate Abe with the value 71. So maybe this is like a table of ages. So Abe is 71 years old. I'd like to say, Abe, you are associated with the value 71. And to do so, I'm going to insert Abe into my table based on the string Abe's hash code, which is telling me it's going to be at index 0. Next, I have the string Brian. Brian has a hash code of 3. So when I try to associate Brian with a value like 99, I'm going to insert the key value pair at index 3 because that's the hash code that gets returned by the string when I invoke it on the Brian instance. Ryan and Joe both have hash codes that map to 2, which tells me that when I try to associate Ryan with 24 or Joe with 48, those associations should be placed inside the bucket inside my array list that is at index 2. An interesting factor here is that Joe here has the same hash code as Ryan. We talked about how hash code can potentially have collisions where 2 values in our generic structure, like Ryan and Joe here, map to the same hash code value. And this is okay because we're using this hashing with bucket strategy where potentially if 2 key types map to the same hash code, they will have the same index inside my array list of linked lists. But because I'm using linked lists inside each row, I'm allowed to append additional pairs onto the end of every row, such that all I have to do is walk the row that contains all the pairs of keys that have the hash code of the index of the row until I find the value I'm looking for. So maybe I'm trying to look up the number associated with Ryan. I visit the second bucket inside my array list, and then I visit each pair inside to go look up the key that is actually value-wise equal to the string that I'm looking up. Maybe I'm trying to look up Joe. I will go to the second index in my array list. I will start walking all the pairs, and I will find the pair that has the key be equal to Joe in order to determine the value associated with Joe. Okay, so that is how our hashing with table strategy is going to work with these hash code functions here. It's going to enable us to map arbitrary values. It's going to enable to map arbitrary values to arbitrary other values, arbitrary keys to arbitrary values by having a hash code that generates me integers for every key. We've talked in the past about how we need hash code modulo size in order to map the hash code method to a range of values inside my table, where hash code returns the natural numbers including 0, and the size is some fixed integer n. So when I do hash code modulo size, I get a range of numbers from 0 to n-1 inclusive, which is indices that I can use for my array list. Okay, so now that we're familiar with how the hash table is actually stored, I want to talk about how hashing is implemented in Java, the language. Every object has a hash code function attached to it that returns the hash of the object, which is a plain integer. With Java library classes, we're going to get a well-defined hash code for free. But just like toString, this method we inherited from the top-level object, the hashcode method is also going to have to be overridden by us, the developer, whenever we write our own class. We can see more details on what the expectations of hashcode are on the official Java Oracle docs for this top-level object. Rather than going to that URL directly, I want to make sure you can get there on your own. If you're looking something up in Java, you should say in Google, Java, the thing you're looking up, and then append 11 so that we specifically get the Java JDK 11 version of the class. I think it typically defaults to something like 7. So definitely make sure that we're picking the right JDK so we get the right API documentation. Anyway, here is the class object docs from Java, Oracle. Class object is the root of the class hierarchy. Every class has object as a superclass. Okay, we know this already. Then when we scroll down, we should go look at the function we're trying to examine. Here we have public int hashcode. Hashcode returns just a plain integer. And we're told that this returns a hashcode value for the object. This method is supported for the benefit of hash tables, such as those provided by HashMap. The general contract of hashcode is as follows. When it is invoked on the same object more than once, the hashcode method must consistently return the same integer, provided no information used in equals comparisons on the object is modified. This is telling us that hashcode should be consistent, it should be predictable. So long as an object remains constant in terms of its underlying value, the hashcode of the object should be the same every time we call it. The next contract tells us, if two objects are equal according to the equals method, this value-wise equality method that we've talked throughout this class, then calling hashcode on each of the two objects must produce the same integer result. So this goes back to that value-wise equality discussion that we were having earlier with our keys inside of our table. If I have two keys that are value-wise equal, they should map to the same object, even if they are not necessarily reference equal to one another. One intuitive way to think about this is with that strings example. If I have two strings, hello world, that are two separate strings, they will not be reference equal to each other because those two strings live in two different spaces in memory, but they are value-wise equal to each other because they have the same underlying characters. If two strings are value-wise equal to each other, they should have the same hash code because I should be able to look up in my table the value that corresponds to hello world regardless of what string I pass in. So this contract is telling me, so long as two objects are equal to one another in terms of value, then they should have identical hash codes. The third contract stipulates it's not actually required that if two objects are not equal to one another, then that their hash code be necessarily unequal. This goes back to that collision discussion that we had. In defining the hash function, we said that we could take the universe of data and map it to integers. And given that we have a limited amount of scope of integers, practically, we will inevitably have a scenario where we have two distinct blobs of data that we pass to our hash function, but map to the same hash value. So I think on the whiteboard example, we saw how two different names could map to the same number. The contract is telling us that this is okay. It is okay if two objects that are unequal don't have different hash codes. Again, if two objects don't equal each other, it is not required that they have different hash codes as well. It is okay for there to be a collision here. And the reason it's okay in terms of our implementation is because we're using that hashing with buckets technique. We enable two keys that have different value that also have the same hash code to be stored in our table because we all just chain them together as part of a linked list. And we will iterate over that linked list in order to retrieve the value that's actually corresponding with the key that we've passed in. We've learned how the hashcode method is going to dictate which table sublist that the object should be stored inside. And the use of a lookup table that contains sublists to store these objects is called hashing with buckets, where each sublist is a single bucket. And we've gone over this on the whiteboard, where we have that array list of linked lists, where each index inside the array list represents an index that corresponds to a given hash code, and then we store pairs of keys and values inside the linked lists contained in a given index. There is a general rule to follow, which is that when you override equals, you should also override hash code. Remember that two instances which are equal to each other should have the same hash code, but two instances that are not necessarily equal each other may not necessarily have the same hash code, or they could have the same hash code. So another way of looking at that is that two instances that have the same hash code may not necessarily be equals. This is that collision scenario where I had two strings that collided in terms of their hash code. They had the same hash code despite not necessarily being equal to each other. So this equality goes one way. If two things are equal, they should have the same hash code. If they have the same hash code, they may necessarily not be equal. They could be equal, but that's not a guarantee. In the pair class, which we've seen many times, if you scroll down towards the bottom, you'll see that I've actually defined a hash code inside this class. So I can use a pair as a key in a hashing table. My hash code definition is left.hashcode exclusive OR of right.hashcode. You don't have to understand how this expression really works underneath. You may not have actually heard of the exclusive OR operator before if you haven't taken a systems course, which is perhaps what you'll be taking next after this one. But here we can kind of digest what's going on, which is I'm deferring my pairs hash code to be the hash code of the value on the left and the hash code of the value on the right, and I'll combine them using the exclusive OR operator. What that means is the hash of my pair is going to be determined by the hash of the left and the right fields inside the pair. And this is where this final keyword really comes in handy. Remember how we had this discussion on how our pair is going to be constant once it's defined, how the left and right fields are going to be defined once and never again? Well, by declaring these left and right fields final, any hash table that's going to invoke the hashcode method as part of using this pair as a key should expect to see some constant value that is returned consistently every time, because the left field is constant and the right field is constant. So I should expect that their hash code return values are the same as well. Now there is kind of a weird exception to this, which is if someone has an outstanding reference to left and an outstanding reference to right and are modifying the underlying values of those references. And therefore, if they change some property inside left or some property inside right that causes their underlying values to change and their hash code definition to change, then this hash code will no longer be a constant value. This is one of those mistakes that the compiler will unfortunately not save you against. The final keyword is not a deep constant keyword. It's only a shallow constant. It's only saying left cannot be reassigned, but it's not saying left cannot be modified. So this is something that you have to be careful of when you have certain assumptions about how people will use your program. So how do hash maps generally work in practice? Well, hash maps do use hashing with buckets, in effect storing a linked list on each table entry, and then pushing an element onto the list with each insertion. Hash maps, like array lists, are going to start with a limited size table. The bucket index is going to be determined by hash code modulo the size. And we've talked about how this modulo operator is going to kind of shrink the space of the output of the expression on the left to be somewhere between 0 and size -1 inclusive. Ideally, every element is actually going to get its own bucket, so we get O of 1 lookup. If every element has its own bucket in the hash table, then we don't have to iterate very far. We only have to iterate over one element when we start to look through all the pairs stored inside each linked list bucket. However, collisions are inevitable. 2 or more elements can be stored in the same bucket, and that is going to start to degrade our performance over time. If our hash codes are not well randomized and they cause this expression to always be heavily weighted towards one value, then we're going to end up storing several key value pairs inside the same bucket, and then every time we try to do a lookup, we have to iterate over several key value pairs inside the linked list, which degrades our performance because there's a lot more iteration that has to happen. The uniform randomness guarantee of hash functions helps us spread out elements across several buckets to minimize the cost of walking each sublist bucket. If hashing is O of 1, and lookup is almost always O of 1 because we spread out all the entries that we're storing inside the hash table across several buckets, then we achieve our goal, which is a generic lookup table with O of 1 retrieval and storage. Let's examine that worst case scenario though a little bit more carefully, where we have too many collisions and we're having too many key value pairs inside of a single bucket. If we tack too many elements inside the hash map, performance is going to degrade to O of n. Over time, if our size remains constant and we pack on more and more elements inside our hash table, we are going to increase the length of every bucket inside the hash table over time. Because even if we have uniform randomness, we're going to keep hitting collisions at some point with large n, and we're going to have to grow the size of every single linked list. Performance is going to degrade to linear time. To avoid this overcrowding, hash maps have something called a load factor that determines when the lookup table needs to be expanded, kind of like when array lists expand when they're out of room. Here's what we're going to do. We're going to allocate space for a new hash map that's twice as large, so the array list of the hash map is going to double in size. We are then going to iterate over all the existing elements, the existing key value pairs. We will rehash their keys based on hash code modulo the new size, and then insert those pairs into their new respective locations. So, kind of like how with the array list, we had to copy all of our elements from the old list to the new list when we expanded it, with the hash map, when we double the size, when we double the amount of buckets we have to go through all the existing key value pairs in all the old buckets and move them to their new bucket locations. By increasing the width of our hash table, we spread out all the existing elements across those individual buckets more evenly. And if we have that good randomness, then they should distribute out pretty well evenly across these new buckets that we've allocated. If we go take a look at the official Oracle of Java docs on HashMap, we can learn a little bit more. Here is the HashMap class in Java. It's got two generic types, a key value and a value type. We're told that K is the type of the keys and V is the type of the mapped values. Hash table-based implementation of the map interface. This implementation provides constant time performance for the basic operations like get and put, assuming the hash function disperses the elements properly among the buckets. So this is the randomization part. Iteration over collection views require time proportional to the capacity of the HashMap instance, the number of buckets plus its size. An instance of HashMap has two parameters that affect its performance: initial capacity and load factor. The capacity is the number of buckets in the hash table, and the initial capacity is simply the capacity at the time the hash table is created. The load factor is a measure of how full the hash table is allowed to get before its capacity is automatically increased. When the number of entries in the hash table exceeds the product of the load factor and the current capacity, the hash table is rehashed. As a general rule, the default load factor is 0.75 and offers a good trade-off between time and space cost. Okay, so let's digest this definition of load factor. Load factor is a measure of how full the hash table is allowed to get before its capacity automatically increases. When the number of entries in the hash table exceeds the product of the load factor and the current capacity, the hash table is rehashed. Remember that the capacity of the table is the number of buckets. So 0.75 times the number of buckets is the number of entries we're allowed to have inside the hash table before we have to expand it. So one way of thinking about this is, in the ideal case, every entry that we have allocated inside our hash table gets its own bucket. So we avoid doing iteration. However, that means we, in the best case, can only occupy 75% of every bucket, and the other 25% of the buckets are going to go unused before we need to start expanding again. Remember, this is still in the best case because we are trying to spread out our key value pairs as best as possible across the most buckets, but the load factor tells us as soon as we hit 75% allocation for the buckets being used, we need to expand again. We are pretty conservative in this number in terms of space we waste. Let me rephrase that. We are conservative in the sense that we will waste a lot of space to attempt to distribute our elements effectively. So it seems like quite a bit of waste to waste 25% of the buckets that we have, but it is intended, designed, so that we avoid having this collision problem, where in the worst case, we somehow get unlucky and insert all of our key value pairs into a single bucket. And then therefore, when we try to look up against a given key inside that bucket, we have to perform a lot of iteration. By having some low load factor value, where the 75% is going to waste 25% of the space potentially, we are hoping that there will be plenty of buckets to go around and that we can distribute our values evenly. This load factor value is going to trade off between time and space costs. If we have a high load factor, let's say something like 0.9, that means we can fill up 90% of the hash table before we start expansion. This minimizes the space wasted potentially, right? It means only up to 10% or 10% or more of the space is being wasted instead of 25% or more. But this also means that there's a higher probability that we are having collisions inside of our key hash codes because we have more entries inside that can fit inside the table before it expands, and there's a greater possibility that two keys map to the same bucket, and then we have more pairs within each bucket. If we shrink the load factor, that is, we make this something really small like 0.2, this wastes a ton of space. At best, we will use 20% of the buckets, and 80% of the buckets will go unused, but then we will very aggressively try to expand the hash table. What will happen, therefore, is we will very likely have tons of room inside of our table, and our table is going to be so wide, the likelihood of collision is going to be really small. We will also waste a lot of space because we will have 80% of our capacity go unused before we expand again. However, we're going to have so many buckets that chances are every single key and value pair that goes into our hash table is going to have its own dedicated bucket, and our lookup is going to be super fast. So here we see a good example of that trade-off between time and space. We can get faster performance if we have more space usage, or we can get more efficient space usage at the risk of greater collisions and slower performance. Your next project is going to feature a HashMap implementation, including this expansion process. So look forward to that. Let's end with some concluding words. HashMaps are magic. We get O of 1 average insertion, retrieval, and removal, contingent on some good hash function. What's the cost? We still have to do O of n iteration. It doesn't have practical ordering like we saw with those list structures or the binary search tree because hashing is inherently random. It can't be sorted for that reason as well. And we also waste space. If our load factor is small, in the best case, we are going to consume all the buckets that up to the load factor percentage, and then we will waste the room of all the other buckets that go unused before we start to expand again. This load factor is kind of like a dial of how aggressively we want to expand to avoid this collision risk. Unlike the linked list or array list, or just the primitive array, which are arguably pretty space efficient, the hash map is always going to have this little extra buffer room to avoid this collision problem and try to guarantee this fast performance that we can do for all these table lookup operations. This trade-off between space and time is one that we're going to see a lot throughout this class. We can consume more space to get a faster algorithm, like how we saw with those optimal sorting algorithms, the merge sort and the quick sort. We consumed more stack space for a more efficient, performant sorting algorithm. Or we could take more time and use less space, like we saw with the naive sorting algorithms, where it took longer for us to sort the list using selection sort or insertion sort, but we could do it using just iteration. We didn't have to consume any additional stack space or auxiliary memory. We're going to see this a lot throughout this course, and you will see it a lot throughout the computer science. And this is a discussion that you're going to have to think about anytime that you write some program where you are limited in one of these degrees. Maybe you have an interviewer that's asking you about making a very efficient algorithm, and you talk about how you might use up more space to do that, using something like caching to store data that you've already computed. Or maybe your interviewer tells you that you have a lot of space. And then in that case, you should definitely have this discussion on taking less time and being more efficient, because you have more room to waste. And you can use these sort of tables like HashMaps, which are less efficient space-wise, but very efficient in terms of performance. Okay, that's a lot to digest for today. Take your time to think about all this. I'll talk to you soon. Thanks for listening.